in the cells in the heart. So the inner parts are negatively charged, okay, and the outers are positively charged. And this is what we called polarized state or polarized cells. Now, through some process, again, we don't need to go in detail like how, okay, I already talked a little bit about that. So through some process, the cells become depolarized. Okay, so depolarized is again the inner ones will become positive, the inner part of the cell will become positive, and outer will become negative. Okay, so if it were not depolarized, and you had to find the potential difference, how would you find the potential difference? So this outer one, you can put a probe on this outer one, okay, near your chest. You can put a probe, and in order to measure the difference, then you will need to make a hole in your heart and then insert in the inner part of the cell. That would be really painful, right? Because you need to connect both this end as well as that end. You can easily connect to this end, it would be on the surface, but this one you need to pierce the cell, okay, to measure the potential. But fortunately, we don't have to do that. Okay, so what happens is when the cells are depolarized, you will have this layer, which is the outer layer, and you have this layer, which is also in the outer layer. Okay, so there is boundary between this positive part and negative part. Positive part from the polarized cells, and negative from the depolarized cells. So that means you don't have to pierce the heart cells. You can just measure on the surface. Okay, so this would be on your surface, and this would also be on the surface. You can put one probe here and another probe here, and then you can measure the potential difference, okay, delta V. You can easily do that without any kind of like piercing or inserting the things in your body. So the way to do that is by using the electrodes. Okay, so you can use these electrodes. There are at least 6 electrodes that are used to measure the potential difference, and it is possible because of the presence of depolarized part and polarized part. So this is still polarized, it's yet to be depolarized, and this is already depolarized, and they are both on the outer part. Okay, like I showed here in this picture. So this is on the outer part of the cell, and that's also on the outer part of the cell. Okay, so this is in the depolarized cell, that's on the polarized cell. So the separation of negative and positive is what we call dipole. Okay, and they have property called dipole moment, which is the product of charge and distance between the charges. Now, during different cycles of your heartbeat, the heart is polarized in different ways. So for example, let's see here. So this is in one particular state. So this is depolarized part and this is polarized part. When you are measuring the potential during this stage, you will get that potential. Okay, part A, this peak A corresponds to this particular state. So the potential between negative and positive is that. Okay, so you have negative here, positive here. So in order to measure this particular potential, you need to put a probe one here and one here. Okay? So these probes or electrodes will measure that potential. And the polarization or the depolarization, it shifts from one part to the other part of the heart. So in the next step, this part will be depolarized. Okay, and this is still polarized. And to measure that, I think you can still use the same probe. So that will measure the potential difference between this region and that region, which is given by this potential. Okay, B tells you the potential difference during this stage of depolarization. And then in the next stage, you'll have most of the upper part of the heart depolarized, and there is this still polarized, yet to be depolarized. Okay, and the potential difference in this case would be measured. I think it should show different probes here, but it's still showing the same probe. So that is the potential difference, okay, in this stage. So the potential difference between the negatives here, that's the negative, and that's the positive here. That is given by that part. Okay, so that's the potential difference for normal heartbeat. Sometimes when you have irregular heartbeat, you may get a different kind of pattern, okay, just by comparing the normal pattern with some other irregular pattern like that. You can tell that something is going wrong, okay, and then you may need to do some kind of treatment. So that's about electrocardiogram. We don't need to go in very, very detail about that. So the next part is capacitors. So what are capacitors? Very important concept. Lots of real-life application, not just in artificial application, but also in our human body. Our cells act as capacitors. Okay, so we'll talk about that. So any two conductors separated by some material is called capacitor. Okay, so you have two conductors. The conductors could be two metals, two aluminum sheet or some kind of metals. Let's say you have two aluminum sheets or some metal plates, okay, and they are separated by some other material. So let's say you put a piece of paper in between two aluminum sheet, okay. So this configuration would be called capacitor. So that's a metal, or you can say conductor, and this is another conductor of the same size, and then there is something in between this. Sometimes you may not have anything in between, but most of the time we have some kind of substance. Okay, it could be either air or water or paper or mica. Okay, we'll have some kind of material in between, and this configuration is what we called capacitors. So the main function of capacitor is to store charge. What you do is you have two plates, two conductors, okay, and then there's something in between the two conductors. I will not write it here. And you connect the two plates or two conductors to a battery. Okay, so battery, the symbol for battery is one long line and one short line. Long line is positive and short line is negative. So the conductor that is connected to positive becomes positively charged, and the conductor that is connected to the negative is negatively charged. Okay, so you charge the plates and then you remove the battery. Okay, so let's say, and then once you charge it, you remove it. You just disconnect the battery. So you disconnect that, and now the charge will remain on the conductor. Okay, so it's charged now, and it stores the charge. So charge stored in the conductors, or we are calling the conductor capacitor. Okay. So we know that whenever there is a separation of charge, there are two things. Can you guys tell me what those two things are? Electric field, exactly. So what else? We can have two things whenever there is separation of charges. One is electric field, that's right. And the electric field for a capacitor is given by Q epsilon naught over A. Okay, so that's the electric field for capacitor. There are different kinds of capacitors. Like one is parallel plate. So you have one plate, another plate. If they are parallel, that's called parallel plate capacitors. Sometimes you can fold this in a cylindrical form like this. So this is called cylindrical capacitor. Sometimes you may also have circular capacitors. Okay, so different types of capacitors are there. So this electric field is for parallel plate capacitor. So you have electric field, it's going from positive to negative. Electric field always goes from positive to negative. So it's going from positive to negative. Okay, so that's the electric field. So that's for parallel plate capacitor. Okay, and the second thing is whenever you have separation of charge, this one is at higher potential. The positives are at higher potential. Let's call that V2, and the negatives are at lower potential V1. And there is, because there is higher and lower, that means there is difference in the potential. So we have potential difference. And how potential difference and E are related? We know there is a relationship between V and E. So we showed last time. E is delta V over distance between the charges, which is in this case, let's call it D. D is the separation, charge separation. Okay, so we have, let's just write this in terms of E. So E is delta V over D. Okay, so we saw two expressions for electric field. Now if E is equal to that and E is equal to that, then these two on the right must also be equal, right? Because if A is equal to B and A is equal to C, then B must be equal to C. So delta v, so Q epsilon naught. So epsilon naught is called permittivity of free space. It's a constant. Okay, so E naught is a constant. Its value is 8.85 times 10 to negative 12 Coulomb Newton per meter squared. That's the value of epsilon naught. It's called epsilon. That's epsilon, and you have a subscript naught here. So that's epsilon naught. So Q is charge. Okay, how much charge you have on each plate. So Q is that. So Q times epsilon naught over A. A is the area of the plate. So that's the area. Okay, how much area the plate has or conductor has. So this is the side view. Okay, if I draw this in a little bit different way, so it would look like that. Okay, from different perspective. So I have two plates, one on the top, one on the bottom, and there is separation of D. Okay, so one has positive and the other one has negative. And if you look from a side, it will look like that. Okay, and this A on the bottom here, that's the area of that plate. Okay, So that's that, and then that would be equal to delta V over D is the distance between the plates. So that's D. Okay. So I can write this as Q is equal to epsilon naught A over D and delta V. Okay. So this epsilon naught is constant. A, if I'm using a particular plate, A is constant. Okay. And D is also constant. I'm keeping the distance same. I'm not changing the distance. So these things, they are constants and they depend on the configuration of the plate. Okay. As long as I keep the area constant and distance constant, this whole thing will remain constant. Okay. So it depends on the capacitor. And that constant is called capacitance of a capacitor. Okay. So this is called capacitance of a capacitor. Now, this is when we are not using anything in between the plates. Okay. So in the example I showed, I'm not using any material. It's a vacuum. Okay. So this is capacitance of a capacitor without anything in between, or in with vacuum. Okay, without anything means there is vacuum. So this tells us like how much a capacitor can store a charge. Okay, so capacitance is its capacity to store charge. Again, the function of capacitor is to store charge, how much charge it can store. Now, if I put a material in between the two plates, what will happen? And why we need to put material in between the capacitors? So you have capacitors or a capacitor, and the main function of capacitor is to store charge. So you connect it with the battery or apply potential difference, and it will store charge. Now, if you have, like in normal case, like you'll have air. Okay, if there's nothing, there is vacuum would be hard to achieve because usually in our normal environment we have air, so we cannot achieve the vacuum. So normally there is air, but air is not a good material to insert in between the capacitor. The reason is when you place the air, when you charge the capacitor, it will charge more and more charges. It will store more and more charges, and at some point the charges will leak. Okay, they will discharge from this positive plate to negative plate. They will start to discharge from positive to negative. This is called dielectric breakdown, and that defies the application or function of dielectric breakdown. So in order to prevent the dielectric breakdown, we need to put something else besides air, like paper or even water or mica sheets. Okay. So what is dielectric breakdown? So basically, when there is lightning, so charges are stored on clouds. Okay. So when there more and more charges are stored on cloud, at some point these charges will discharge, okay, flow into the ground, which we call lightning. Okay, this discharge is what is the example of dielectric breakdown. So that's also dielectric breakdown. So when there is air, these things can only hold so much of the charge. Okay, once it crosses that limit, it discharges the charge from one side to the other side. So we want to prevent that in the capacitor because we want to store more charge. Okay. So what we put in the in between the plates. So lots of things we put, okay, like we may have Teflon. It's right here. So the things we put in between the plates are called dielectrics. Dielectrics or dielectric material. Okay, so such as Teflon, sometimes paper, Pyrex glass, water, okay, those kinds of things. Now, when we place the dielectric material, then the capacitance would be modified. So in case of vacuum, when there is nothing in between, the capacitance is given by C is equal to, if you go up, you can see this is the capacitance when there is nothing, epsilon naught A over D. But with the dielectric material, it would be now this kappa, which is the property of the dielectric material, epsilon naught A over D. Okay. So this kappa is called dielectric constant. It basically increases the capacitance of a capacitor. Okay. It doesn't allow the dielectric breakdown to occur at smaller voltage, meaning it can hold more charge. So these materials have different dielectric constants. So the dielectric constants for Teflon is 2. For air it's about 1.00054. For vacuum, it's 1. Okay, so when you put 1 in this, it would be the capacitance for vacuum. For paper, it's 3. Pyrex glass is 4.8, and water is 80. So water is a very good dielectric material. Okay, it has dielectric constant of 80. So that's all we need for capacitance. With that, we can solve all the worksheet problems and homework problems. But one more thing, okay, and then we can solve all the problems. So whenever you are storing charge on the capacitor, it's also storing the energy. Okay, so storing charge means you are storing electrical energy. So storing charge means you are storing energy. In this case, it's electrical energy. So how much electrical energy you store in the capacitor? It's given by this formula. Okay, so energy stored in a capacitor is given by U is equal to 1 over 2, 1/2 C, that's the capacitance, and delta V squared. Delta V squared is the potential you apply across the capacitor. So you connect it to a battery. Okay, so that's the potential difference of the battery, delta V. Or you can also say this would be same as, also same for the potential difference across the battery, across the capacitor. So there will be potential difference here. That potential difference would be exactly same as the potential difference of the battery. Whatever potential difference you apply through the battery, same potential difference would appear on the plates. Okay, so now let's look at the questions. So let's see the worksheet problems first. So worksheet problem, let's see if I could download that. Let's look at the number 1 of the worksheet problem. That's pretty straightforward. Just applying the formula, there is nothing. Let's see where worksheet. Okay. So basically, you are given the capacitance, which is that capacitance is measured in unit called farad. Okay. So F is farad. Capacitance has the unit of farad, F. So we are given the capacitance, and then we are given the delta V. Okay, that's the potential difference that you are applying across the capacitor. So how much charge is stored in the capacitor? Okay, so one is charge. When you are charging it, how much charge is stored, and then how many electrons is that? So let's look at that. It's number 1, worksheet 7. So we want to find the charge Q, and Q is given by C delta V. Okay, capacitance times delta V, where capacitance is epsilon naught A over E, sorry, epsilon A over D. So when it doesn't say, when the question doesn't say what material is used between the plates, then you just assume that it's vacuum. Okay, if it says it's paper or plastic or water, then you need to consider the K here. But if it doesn't say anything, just use this one. No need to use K. Okay, so capacitance is 3 times 10 to negative 14 farad, and delta V is 5 volts. Okay, that's pretty straightforward. You just multiply that. That'll give you 1.5 times 10 to negative 13. So Q is measured in coulombs. That's Coulomb. And then we also need to find how many electrons is that. So 1 electron has 1.6 times 10 to negative 19 coulombs of charge. So we need to do a little bit of arithmetic here. So if 1 electron is that much coulomb, then 1 coulomb would be 1 divided by 1.6 times 10 to negative 19 electrons. Okay, so that means number of electrons would be that, okay, coulomb, and 1 coulomb is that many electrons. Okay, so that would be the number of electrons. So that's number 1. Let's look at number 2. What capacitance would you need to store 1 coulomb of charge on 2 plates at 120 volt? And that's again the use of same formula. So C is, again, Q is C delta V. So we want to find capacitance in this problem. So C would be Q over delta V. Q is 1 coulomb. Delta V is 120 volts. Okay, so that will give you the capacitance, which is in farad. Okay, and then the next part is, if the closest that we can get the plate together is 1.01 millimeter, so we have 2 plates, and the closest we can get means the distance between the 2 plates is 0.010 millimeter. Then what size of the plate we need to achieve that charge? Okay, so we want to find the size, means area. That's part A. So for part B, capacitance is given by epsilon naught A over D. Again, if the question doesn't say what is in between the plates, you just consider it's vacuum, or there's nothing. Okay, so we want to find A, so write this in terms of A. So A would be C D over epsilon naught. Okay, C is whatever you get from here, so 1 divided by 120. One divided by 120. is 8.33 times 10 to negative 3 farad. D is the distance, which is 0.010 millimeter. Turn that into meter. And then epsilon naught is a constant. Its value is 8.85 times 10 to negative 12 Coulomb Newton per meter squared. Okay, and do that calculation. That will give the area in meter squared, because it's meter squared here. C is what size plate would we need if we fill the space between them with Pyrex or water. So we need to do for both actually. So let's do for Pyrex. Okay, if you fill that with Pyrex, now the new capacitance will be C is kappa, okay, K or kappa, epsilon naught A over D. So we need to find the area. Area would be Ca kappa epsilon naught. C is again same as before. So we want to get this capacitance. And then, area is what we need to find. So area, that's CD, that's C times D. Okay, so we are multiplying C by D. On top we have CD, and then on bottom we have kappa and epsilon naught. So that's 8.33 is C. D is the separation, and then kappa, because we are using Pyrex, for Pyrex kappa or K is 4.8. So 4.8, and then epsilon naught is 8.85 times 10 to negative 12. Okay, so that will give you the area in meters squared. Now for water, if you want to use water, then kappa would be 80. Okay, do the exactly same thing, but the value of kappa would be 80. Okay, so let's look at number 3. It's pretty straightforward, just applying the formula. Okay, there is nothing complicated here. So number 3, let's read that. So it says that you have two parallel plates. Okay, so you have a plate here and a plate here, and the area of the plate is given. So area is 20 times 30 centimeters squared. Okay, that's the area, and they are separated by 1 millimeter, and there is air in between the plates. Okay, air. If it is air, we can just say kappa is 1. Okay, it's almost like vacuum. There's not much difference. And then the plates are connected to a battery that has the potential difference of 12 volts. So the first one is calculate the capacitance C. Okay, C is just the formula, applying epsilon naught A over D. Epsilon naught is 8.85 times 10 to negative 12. A is 20 times 30, and then you need to change that to meter squared, so that would be 10 to the negative 4 meters squared. And then the distance between the two is it's millimeter, not meter. Millimeter means 1.0 times 10 to negative 3 meter. So do that, you get the capacitance. And B is charge. That's also pretty straightforward. So Q is C delta V. C is capacitance, whatever you get from here, and then V is you're applying 12 volts. Okay, so that gives you charge in coulombs. What is the electric field between the two? Okay, so this would be positively charged because this is connected to positive, and this would be negatively charged, connected to negative, and there is electric field in between. So the electric field is given by, we know the formula, delta V over D. Delta V is 12, D is 1 millimeter, and that gives you E. E is measured in Newton per Coulomb. You can also say volt per meter. Often it's used Newton per Coulomb. Estimate the area of the plate needed to achieve the capacitance of 1 farad. So capacitance is epsilon naught A over D. Again, there is air. Air means you can say it's vacuum, kind of vacuum. Not exactly vacuum, but more or less like vacuum. So we want to find the area. So write this in terms of area. So that would be CD over epsilon naught. Capacitance we want to achieve is 1 farad. Gap is 1 millimeter. And epsilon naught is constant, 8.85 times 10 to negative 12. That will give you area in meters squared. Okay. Now let's look at number 4. So it's asking to find the energy stored in a capacitor. So you want to find the energy stored in capacitor. So the capacitor has capacitance of 150 microfarad. Micro means 10 to negative 6. And you apply voltage of difference of 200 volts across the capacitor. So how much energy is stored in the capacitor? It's given by 1/2 C delta V squared. Apply that. Capacitance is 150 times 10 to negative 6 farad. Delta V is 200 volts squared. The unit for energy is joules. Okay, joules. Okay, so let's look at number 5. So you have two plates or a parallel plate capacitor. They are separated by distance d, and you connect it to a battery. When you connect it to a battery, you will charge the capacitors, and let's say it acquires the charge of Q. Now you remove the battery. Okay, once you charge it fully, get rid of the battery. So it's fully charged, so get rid of battery. Now the potential difference across this would be the potential difference of the battery. It will have the same potential difference as that of battery. So let's say that's delta V. Okay, its value is not given. Let's just say it's delta V. Potential difference. Now, if you double the separation, okay, so this will store some energy. Let's call the energy stored in this case is U1. Now you double the separation distance. Okay, I don't have space. So let's double the separation. Now it's 2d. There's no change in delta V and charge. It's still same. We didn't do anything with the charge. Still Q. The only thing we did is we doubled the separation. Now, how will that change the stored energy? So how this energy compared to, how is this energy compared to this energy? So we need to find that. Okay. So energy is 1/2 C delta V squared. Okay. let's call this U1 when the separation is D, and then let's call this one U2. U2 is that, and why I'm writing C1 and C2, because C is epsilon naught A over D. It depends on the distance. Okay, when I change the distance, I change the capacitance. So I need to write different capacitance here because we are changing the distance. But why I am not writing subscripts for delta V? Because delta V is same. Okay, I'm not doing anything with delta V. It remains same. So divide U2 by U1 on both sides. So 1/2 C2 delta V squared, 1/2 C1 delta V squared. So delta V and delta V are same, cancel that, half and half cancel. So C2 over C1, U2 U1. Now C2, we have this formula for C is epsilon naught A. A is same. Okay, I'm not changing A. The area is same. What I'm changing is only the distance. So A is same, but let's call D as for C2. Let's see. Yeah. So so delta V is basically, it's, we don't know about delta V. Okay, there is no information. The only thing we know is Q. Q doesn't change. Okay, it doesn't say whether delta V changes or not. So the best thing would be, so instead of considering delta V to be same, the best thing would be to write this in terms of Q, because we know Q is same. Okay, Q doesn't change. I'm a little bit suspicious about delta V because it doesn't say whether delta V changes or not. So I'm going to write this in terms of Q. Okay. So instead of that, let me write U1 as 1/2 C1. So we know that Q is C times delta V. Okay, that means delta V would be Q over C. Okay, so I'm going to write this formula, this top one, in terms of Q. Okay, delta V is Q over C. In this case, it's C1 squared. Okay, so that's 1/2 Q squared, and then we have C squared here and C here. One of the C's would be cancelled, so that would be C1. Okay, and then U2 would be 1/2 C2 delta V is Q over C, so Q over C2 squared. Okay, again one of the C's would be cancelled, so I would be left with Q squared over C2. Okay, that's the Q1 and Q2. Now let's divide U2 by U1. So U2 over U1 is equal to 1/2 Q squared C2 over 1/2 Q squared C1. Okay, so these things are same, so we can cancel that. So C2 over C1. I think it will give same result even if I do that. Okay, so it's the same result. Okay, so I was a little bit suspicious about the voltage, but it gave the same result, C2 over C1. So there's no problem. So C2, we know C is epsilon naught A over D. Okay, so epsilon naught A is not changing, D is D2, and then C1 is A over D1. So that cancel. So U2 over U1 is, so this D goes on the top, so D1 over D2. Okay, so D1 is, let's say D1 is D, okay, and D2 is, we double the distance, so 2D. Okay, so D1 is D and D2 is 2D. So D and D cancel, so that's 1/2. So U2 would be equal to 1/2 U1. So energy decreases by 1/2. Okay, when you increase the gap, energy decreases by 50%, 1/2. Okay. Okay. So homework questions, mostly they are similar to the ones I just did. Let me real quickly show you number 5. Okay, we still have 3 minutes left, so I'll show you number 5 from homework. Okay, so you are connecting a capacitor with a paper dielectric to a battery. So you have capacitor, so you connect it to a battery, okay, and you charge it. So when you connect it to paper, you can it can hold the charge of 4.4 nanocoulomb. Okay. Now if you connect it, if you put, so when there is paper, you can store that much charge. If you put Pyrex, then how much charge it can hold? Okay. So for paper, that much charge it can hold. For paper, Pyrex, what's the charge it can hold? So let's find that out. So Q is C delta V. So let's say this is for paper. Let's call this Q1, and that's Q2, Q1. And Q2 for Pyrex, it would be C2 delta V. Delta V is same. We're not changing the delta V. Okay. And when there is dielectric, C is given by kappa times epsilon naught A over D. Okay. So for this one, we can write it as Q1 is equal to kappa epsilon naught. That's 1. Area is same for both, and D is also same. The only thing we are changing is the dielectric material. Okay. Area and D are same. And for Q2, we can write K2 epsilon naught A, same thing again, and D. Okay. So let's divide Q2 by Q1. Q2 is kappa 2 epsilon naught A over D. Q1 is kappa 1 epsilon naught A over D. Cancel all these things, they are all same. Okay. The material is different, but area, distance are same. So Q2 would be Q1, if you do the rearranging here, Q2 over kappa 1. So Q1 is, we can store 4.4 nanocoulomb in Q1. K1 is paper. So paper has dielectric constant of, what was that? I think it's 3.7. Okay, 3.0. Okay, 3.0. And Pyrex has dielectric constant of, is that 4.8? What? Okay, 4.8. Okay, so you do that calculation, that will give you how much charge would be stored if you use Pyrex. Okay, that's nanocoulomb, because we have nanocoulomb, still nanocoulomb here, so the unit would be nanocoulomb. Okay, I think we are out of time. try the homework. If you still have questions on the homework, you can send me email. We can do the homework on Monday also if you have any question. Yes. Yeah, I already posted the practice test. You can look at that, and I also posted the partial key for that. Okay, so you can find it here. So that's the sample exam, and then I'll also post the key. Yeah. And if you guys have any question, you can send me email or come Monday to ask the question. The exam is Monday at 2 during the lab time.